Okay.
Wait, that's bio.
Number 21 on the AP review. A solution with a volume of 1 liter has a pH of 3. What volume of water must be added to the solution in order to raise the pH by 1 unit? Okay, so we need it to go from pH 3, which is 10 to the negative 3, concentration of hydrogen. And we need it to go, if we want to raise the pH by 1 unit, that's going to be pH 4, which is a 10 to the negative 4 concentration of hydrogen. So that is a 1 in 10 dilution. Does that make sense? We're diluting it 10 times diluted. And if it's 10 times diluted, you need the solution to be 1 liter in 10 liters. Yeah? Because what we've got here is we have 10 to the minus 3 molar. And we will multiply by that by the original concentration. That will give us moles, right? This part here would give us moles. And then we would divide it by the new volume. Does that make sense? Or you can use C1V1. That's a good question. It's probably just in that random pile of paper over there. Because I just put things there on Friday. So. There you go.
If you add them now, you just need these concentrations are right. And then this one's concentration okay, this one should yeah, so this one will go down. And then the piece would then because you added the ones. So there's for I finished the review today. I don't still have a lot of it's not fun. Wait, where did she go?
Okay. Are you guys familiar with this formula? We might have used it last year as M1 V1 equals M2 V2. That is the magic formula, yes. And actually, it was really funny. I was just talking to a student who is just graduating from U of T, got out of AP Chem, 4 or 5 years ago at this point. And she said, out of all the things that she uses all the freaking time, that's the one.
Did she come in?
Yeah, she did some stuff in chem. What is she doing right now? She's doing stuff with stem cells. Yeah, so she's doing they're trying to develop stem cells into heart pacemaker cells. So instead of having an electronic pacemaker in the heart, you could actually implant pacemaker cells and then have it grow into a region of the heart that keeps pace for the heart on its own, right? She says, they're years off still, but that's what they're working on. Anyway, she's applying to do her PhD now, and she says, and you know what she looked like when she was in grade 12? when she was taking her tests and getting her tests back and stuff? So don't you worry, you will be fine. Okay? Her grades were not like the best grades ever. Like they were good, but they weren't like, top of the class or anything. Right? So you guys will be great. Okay? Yeah, you two will be out doing amazing things for this world. All right. Or not, and it doesn't matter if you decide not to do amazing things for this world, that is okay too. If you choose to just earn a living and support yourself and be happy in this world and be happy with the people around you, that is also just perfectly fine. You do not need to, cure cancer, save the world, develop a natural pacemaker. You don't need to do any of those things to be amazing people, okay? Just remember that. Because I know we all put a lot of pressure on ourselves, right? And you need to remember that as long as you are, being a good human being and looking after yourself and others, that there is nothing more that this world needs from you. Okay? All right. Anywho, let us go back because she did say M1V1 equals M2V2. That is our magic formula. And you can say, okay, I need to know what volume of water has to be added. So that's going to be, I want to find V2. So V2 is equal to M1 V1 over M2. All right. And we get M1, 10 to the minus 3. M2, 10 to the minus 4. V1, 1 liter. And so that's going to be 10 liters. Now, it doesn't say what is my final volume. It says how much water is added. Yes? So how much water has to be added to get from 1 liter to 10 liters? 9 liters. Is good? Cool. Yes? Okay, so for KW and PKW, if you choose to write 1.0 times 10 to the negative 14, you have 2 sig figs and that will limit your calculations. Yes? If you choose to write 1.00 times 10 to the negative 14, that will have 3 sig figs. And that will perhaps limit your calculations. PKW can be 14.00, or you can write it as 14.000. Your choice. Okay? But just those ones. And on AP, I don't know. What do they say? They say 1.0. So you're limited in AP to the 1.0. Okay. And for PKW, they just say 14. So you can just be like, go with whatever you have in your other numbers. Yes? I would go with 2 sig figs because this is 2 sig figs and I'd be like 14.00 would make sense to me. But yeah, I don't mind either way. Okay, good question. All right, what am I doing? I don't want solubility. I want that. Other questions from either of the reviews? Yes.
I forgot.
Yes.
Oh, wait, no. I thought I had a question, but I remember that I actually have.
Okay. Well, that was easy. Yes. 6. Same. All of the following can act as Bronsted-Lowry bases, except, I'm not sure I love that question. Because I really feel like it's those two. Yeah. I don't love that question. Cross out number 6 for the AP. Yeah, because it could be D or E. Don't love the question. Yep, on the AP review.
You did a regular review.
Yep.
7, the written one.
Number 7 written from the regular review, yes. Yes. Cannot. There were the answer. It was asking which one cannot be a Bronsted-Lowry base, and I would say NH4 plus and Cl minus would both satisfy that. So it's a poor question. So I need to get rid of it. Yeah. All right. Oh, what happened? Where'd it go? There we are. A solution with a pH of 4.20 is found to contain twice as much conjugate base as acid. So we have HA in equilibrium with A minus plus H3O plus. Yes. And we know that the pH is 4.20, so concentration of hydronium is equal to 10 to the negative pH, which is 10 to the negative 4.20, which is 6.3 times 10 to the minus 5 molar. Okay, so this number here is this is my equilibrium. I'm not bothering with the other ones because I don't need my initial and all that stuff. This is my equilibrium row, 6.31 times 10 to the minus 5. What else could we know from that? Okay, let's go back and write the ICE. Why are you not erasing? There we go. ICE. 6.31 times 10 to the minus 5. Yep.
Oh, and then you have the X minus.
Now,
You have the X with initial for HA.
wait. Read the question carefully. Twice as much conjugate base as acid. Twice as much conjugate base as acid. What is my conjugate base? Conjugate base. Twice as much of that as you have of acid. So what would acid be? Half of that. 6.31 times 10 to the minus 5 divided by 2. So we would get then Ka equals A times H3O plus over HA equals 6.31 times 10 to the minus 5 squared divided by 6.31 times 10 to the minus 5 divided by 2, which is the same as if we get rid of that and we multiply this by 2. Yes? We're good with that? And this is going to cancel with one of those. So it'll be 6.31 times 10 to the minus 5 times 2. 6.31 e negative 5 times 2 is 1.26 times 10 to the minus 4. Is that what the answer key says? Number 7? Except for there would only be 2 sig figs, 1.3 times 10 to the minus 4? Yeah, okay. So that one's kind of like just about reading the question and being able to interpret like what it's actually, information it's actually giving you. Yes? 11A for the written. What does 11? Okay. The predominant reaction is the one that happens the most. That's the favored one. So what you have is you have an acid mixed with or a base, right? Because that one's amphiprotic, mixed with, what is HSO4? Is it acid, base, or amphiprotic? It's only an acid. Why? Why is it not amphiprotic? Its conjugate acid is strong. So what that means is that HSO4 must act as the acid, so that is the predominant reaction. So the predominant reaction is just HSO4 minus, I would think this would be a better question if they gave you two actual amphiprotic things and made you compare their Kas. So maybe it would be better if that was HSO3, but yeah, I guess you compare with HSO4. I'm going to change this next time to make that HSO3. Change to HSO3 minus. Does that make sense? Cool, cool. Other questions? Yes? No, nothing. Everything's on there. Yeah. Let's just double check, make sure there's no weird questions in here. No, that's fine. No, that's fine. No, that's fine. That's fine. Oh no, those ones would all be fine. It's this one I should be looking at. Let's see. X. Remove. I think that's it. I think we're good. Oh, the only one that wouldn't be, this is the only one that would be AP only. That is number 31 on the AP review. Huh? Why would that be? Because it requires you to multiply your Ka values. It's just, it's not that it couldn't show up, but because it sort of involves that addition of reactions, it's unlikely. Yes? It means it's not going to be on your test on Wednesday. Everything else could be. Because all the rest of them are not. Yeah, no, all the rest of them are fair game. Yep. Yes, yes.
Can't find the exact question, but it was like relating the KW with the pH, how the pH of the water changes as the temperature changes.
Yes. Okay. So as we increase temperature of water, we will find that the pH decreases. Okay, and you would do that by like sticking a pH meter in it. Yes? We know this through observation. pH meter. So from that, I could ask you, is the autoionization of water Endo or exothermic? So what we've got is we've got this, which doesn't matter. We've got our initial, and this is 10 to the minus 7, and this is 10 to the minus 7. And if the pH decreases, what does that tell us about the hydrogen? H3O plus increases. So these are going to go up. Yes? By some amount. We don't know how much. Yes? So this will be like, I don't know, 10 to the negative 6. I'm just going to make up that number. Yes? Okay, because it's not going to be actually that number, but it'll be something like that. It's going to be a bigger number. Okay, so which way has this equilibrium shifted? The equilibrium has shifted right. So what has happened? Which side is the heat term on? Yeah. I feel like we've talked about this several times. Yes, we have. Yeah. Okay, so the system has shifted right because when we increase temperature, the system shifts. Oh, shifted right. When we increase temperature, the system shifts. This is a new sentence. To absorb heat to bring the temperature back down. Yes? Therefore, the heat term must have been, therefore the endothermic reaction must have been the forward reaction. Or you could say, therefore, the heat term must have been on the left-hand side. Okay? Left-hand side. You guys are okay with LHS for left-hand side? Okay, excellent. All right, so we've got that. What then happens to Ka? Or sorry, Kw. When temperature increases. Kw increases because we shifted to the right. What happens to concentration of OH when temperature is increased? It increases because we are shifting to the right. Are the hydrogen and hydroxide still equal to one another? Yes. You don't need to write any of this stuff. I'm just giving you all of the, somebody said, let's go through the whole thing. So I'm giving you everything. Yes? We're going through the whole thing. Is the water neutral? Yes. Are the pH and pOH higher or lower than before? Is one of them higher and the other lower? They will be equal. Okay, so they're still equal. Are they still 7? No. Are they greater than 7 or less than 7? Remember, our concentration of H plus and concentration of OH minus, are those greater than 10 to the negative 7 or less than 10 to the negative 7? Greater than 10 to the negative 7. So what kind of numbers would be greater than 10 to the negative 7? 10 to the negative 6. What pH would that give you? 6. So the pH would be less than 7. And the pOH would be? Yeah, pH is less than 7. pOH is also less than 7. So what do pH and pOH equal? pH plus pOH in this case would equal 12. So pKW would be 12. Now you're not going to get nice numbers like that. You're going to get something like, I don't know, 4.8 times 10 to the 7, which is bigger than 1.0 times 10 to the 7. But you just throw it in your calculator, right? Do we feel like that was sufficient? Yeah? Okay, cool. Anything else? Yes? AP number 8. All of the following are true of bases except this is, I don't like this one. Toss that one. Omit. Because there's a third type of base that we have not talked about, but it's not in the AP curriculum anymore. Those are Lewis acids and bases. And that has to do with the ability to accept electrons or donate electrons, and we're not going there. Okay?
That's not why, I saw, someone acids.
Yeah, Lewis acids and bases, that's your third type of acid and base. And we used to have to know it, but we don't anymore, so omit this. Okay? Okay. Anything else?
If you increase the pH, it would get more acidic.
Hang on. So if we increase pH, what I'd like you to do is I would like you to say, if I increase pH, let me write down an example of what that would look like. That would look like going from 7 to 8. What is my hydrogen ion concentration if I go from 7 to 8? That's 10 to the negative 7 to 10 to the negative 8, which is getting smaller. Don't be shy about writing really simple examples for yourself using simple numbers, because that makes it really concrete as opposed to just this abstract idea, right? Yeah? pH and hydrogen go the opposite way from each other. One goes up, the other goes down. Same thing with pOH and hydroxide. One goes up, the other goes down. Yeah.
And then if it's greater than 7, it's basic, right?
At 25 degrees Celsius, yes.
Yeah.
If it's greater than 7, it's basic.
And
If
then-
it's less than 7, it's acidic.
So when the temperature increases, the pH would increase, right?
When temperature increases, what happens to hydrogen?
It would increase.
Hydrogen increases. Okay, so we have heat here. This increases. This shifts over this way. Hi. No worries. Poppy donations.
Coming back, so if I just remember saying, coming back each day, each period through this week, and reflecting the basis of the rule of evening.
Excellent. Thank you so much. Anyone have a donation today? Apparently not today, but you'll be back all week, right? Yeah. So let's try and support that as we go forward during the week. It's kind of nice to be able to do that. Yeah. All right. Thank you so much.
So when the temperature increases, does it always add to the reaction side?
When the temperature increases, it increases. Oh, either way, it doesn't matter. Yeah. When the temperature increases, all the water increases in temperature. These particles move faster and these particles move faster. You cannot add temperature to one side of a reaction.
Okay, so when you're, so both of them would increase.
So both of them increase. What happens, both of them move faster. What that means is that the system says, whoa, slow down, particles. So what's going to slow down the particles? Absorbing heat. So we're going to shift in the direction which absorbs heat, which will bring the temperature back down and make the particles move more slowly again. Yes?
Okay, that makes sense, yeah.
Okay.
And then,
And as we shift that way, we are making more hydrogen.
right,
What happens to the pH?
since hydrogen is increasing, it goes down.
Yeah.
Because if hydrogen increases, right, because going from -7 to -8, -8 is tinier.
Yes.
So pH would go down.
Hang on. Yeah.
Yeah. Okay. I think I got it.
I think. But it would go from 10 to the -7 to, say, 10 to the -6, right? So pH would go from 7 to 6.
So it would go down.
So pH goes down. Yes. Yeah. Okay. Hi. Uh-huh.
I know when you say that it shifts, right? Because it needs to like absorb heat to bring the temperature down. But like, is it another way that you can tell that it shifts, right? It's because like the concentrations of the product increases.
Yes.
So it's like shifts, right?
Yes. Yes. The only reason you'd bring that other argument into it is if you were asked, is it endothermic or exothermic?
So that explanation also works.
It also works, but not if you're saying, is it endothermic or exothermic? Yeah, you can say my products increased, therefore it shifted right. And since the temperature increased and it shifted right, the forward reaction must have been endothermic to absorb that extra heat. Yeah? Yeah.
I'm sorry, hearing.
Yes, they are. Other questions?
For
Yes.
Water.
Mm-hmm.
Like, if it's pure water or just water, is it the same that it's always neutral?
Yeah.
Like, some question is like,
It doesn't, I always say pure water, but if you just say water, if you have some water, you can assume it's pure in a question. Yeah, you know what I mean? Otherwise, they'd say you have a solution of something, right? That's not water, right? Yes, Brian.
It's just like a
Yep.
For this event, like, on this, what do you think people like tend to get wrong?
Sometimes people, okay, but this doesn't seem to be a problem with you guys. But I will say that sometimes people will use a rice table when they have a strong acid or a strong base. Sometimes they will not use a rice table when they have a weak acid. Yes? And then, of course, there's sig figs all over the place. Sig fig, sig fig, sig fig, sig fig, sig fig. Yes? Those are the big ones. Yeah. Same as before, 24 MC, 16 written response marks. Marks, not questions. Okay, so it's out of 40. And yeah, that's it. Other questions? Going once, going twice, going 3 times. Sold. Let's move on to solubility. Okay. You didn't get your new book yet, did you? Okay, let's grab you a new book. Okay. Now, where did we leave off last day? Okay, so we left off with some qualitative analysis stuff. I'm going to let you do some of those for homework today, and we are going to start on, hang on just 1 second. Yeah, okay. We're going to look at an introduction to solubility equilibria. This is on page 23. So solubility, this is our temporary definition. This is a very qualitative definition, is the degree to which a solute will dissolve in solution. How much will dissolve, basically. When we first discussed solubility, we learned that some ionic compounds are soluble and will completely dissociate. Okay, so if it's water soluble, it completely dissociates. We also learned that other ionic compounds are water insoluble and will not dissolve in water at all, remaining completely in the solid phase. So here are our water insoluble compounds. And back in grade 11, we were like, close enough. It just will not dissolve in solid. And if you were to mix 2 of the ions together, you would get a precipitate. Yes? But we are adding on to that now in grade 12. And I think we did a little bit last year as well. This just sitting there and not having any dissolved particles is an oversimplification. A little tiny bit will actually dissolve. Yes? So we have a tiny bit actually dissolves. Yes, that's why it is low solubility, not insoluble. Yeah. So they will actually dissolve a very small amount. All right, and we've already mentioned this. Substances which dissolve this way can be communicated by a solubility product constant. So we have the solubility product, KSP. And what 2 things are we multiplying to get the product? We are multiplying the concentrations of the ions. Okay, so let's say we have a salt like AgCl, which is really nice because it's a 1-to-1 ratio, not very complicated. It will dissolve in water and form a dynamic equilibrium. So for some ions dissolve, other ions rejoin. Okay, so we get dissolve, we get rejoin, and overall the concentration remains the same. Yes? So we had here 4 dissolved particles, yes? 2 more dissolved, but then 2 of the other ones precipitated, so we end up with a net still 4 particles. Does that make sense? Are we good with that? These happen simultaneously. The dissolving and the reprecipitation. Okay, we know we are at equilibrium because the concentration, which is a macroscopic property, remains the same. And the concentration remains the same because the forward rate, in other words, the rate of dissolving, is equal to the reverse rate, the rate of precipitation. So forward is dissolving, and reverse is recrystallization, and those 2 rates are the same. So it is an equilibrium. So here is our KSP, and we always write the solid on the left. Solid on the left for KSP related questions. Do you guys remember what I called this thing? This equation? It was called the solubility equilibrium equation. In other words, I'm going to refer to it very often as the SEE, the SEE. No one else uses this term. This is just a Ms. Spence thing. If you want to use that, you can certainly define it if you're writing like an explanation. And then you can put in brackets SEE and then use that going forward in any explanation question. But chances are you won't have to. Mostly you're just writing it. You're just writing the solubility equilibrium equation. You're not referring to it, okay? So we have AgCl, which is water insoluble, which really means low solubility. Okay, and of course we have our equation, and it has coefficients of 1 and 1. So our KSP has exponents of 1 and 1, just like every other KEQ that we have dealt with so far. Right? The coefficients become the powers. And just like any other KEQ, do we include a solid? No, so we don't include the solid. And there we go. That is what KSP is. Okay? So nothing really particularly new. By convention, we always write the solid on the left because it makes the math easier. If we were to write the solid on the right, number 1, all the tables would be different than they are now. And number 2, the math would just be harder. So that's why they chose that the standard is going to be solid on the left. Is good? Okay. Interlude. The C, the SEE, versus the precipitation equation. I'm going to call that the PE, which unfortunately looks a little bit like potential energy. But once again, it depends on context, and you're not going to be writing about the PE. You just need to recognize when to use it. When do you use a precipitation equation versus when do you use a solubility equilibrium equation? When we write a solubility equilibrium, the solid goes on the left. Solubility equilibrium, the solid goes on the left. Okay, that's our C. When we write a precipitation reaction, we are looking at the process of forming a precipitate. So who should be the product? The solid should be the product, because we are, for a precipitation reaction, we are forming a precipitate. So the product is the precipitate and the solid goes on the right. So for our precipitation equation, the solid goes on the right. I'd also like you to take note of the different arrows. If we're doing a solubility equilibrium equation, what kind of arrow should we use?
Double harpoon.
Yeah, double harpoon arrow, an equilibrium arrow. Because it is an equilibrium. When we're looking at a precipitation, we use a one-way arrow because we're really just concerned about forming that precipitate. Perhaps later on, we will then think about the solubility equilibrium, but then we'll write that equation separately in the solid on the left way, okay? So anytime we have a precipitation reaction, we have a one-way arrow. So later on, we will look at situations in which a precipitation occurs. So we have a precipitation occurs, and then we have an equilibrium set up. So we have precipitation, A plus B gives AB solid, one-way arrow. And then an equilibrium is established, AB solid in equilibrium with A and B, and that'll allow you to do some KSP calculations with it, okay? Be sure to always write the equation in the correct direction using the correct arrow. You will lose marks if you choose the wrong one. So we are going to take a look at a few questions. Okay. Write the net ionic equation. So we're going to decide whether we're going to use the PE, the precipitation equation, or the SEE. And then we're going to write the actual equation. So we want to write the net ionic equation that occurs when equal volumes of 0.2 molar barium chloride and 0.2 molar NH4,2SO4 are mixed. Is that going to be a precipitation equation or a solubility equilibrium equation? That's going to be a precipitation equation. Yeah, we're like, ooh, I have these two solutions. I mix them. I get a precipitate. What's the reaction? So this is a precipitation equation. Could you please write the net ionic equation that occurs when we mix barium chloride and ammonium sulfate? So if you're like, I don't know where to go from here, you can combine your outside ions, which are the barium and the sulfate. You can combine your inside ions, which are the NH4 and the chloride. Out of those two, is there one precipitate, two precipitates, or no precipitate? One precipitate. Who is it? BaSO4, because all ammonium salts are soluble. Yes. Okay, so this is going to be our solid. This is our precipitate. This is going to be aqueous. So our net ionic equation then, we want to make the solid BaSO4. Who would the two reactants be? Ba2 plus SO4 2 minus. Excellent. All right. The molar solubility of PbI2 is 1.52 times 10 to the minus 3 molar. Calculate the value of KSP for PbI2. Which should we use, the PE or the SEE? This is a KSP question, so we're going to use the SEE. So could you please write the SEE for this? If we needed to calculate the KSP, what tool do you think we should use? What the heck, why don't we just do this question while we're here? Now what I'm going to do is I'm going to put the molar solubility of PbI2 in brackets, 1.52 times 10 to the minus 3, because of course PbI2 is a solid. Yes? How much of the PbI2 dissolves? The molar solubility is how much dissolves. So if this is how much dissolves, what? Really, all you need to be able to do for this question at this point, because we're not really on section 3.3 yet, is you need to be able to write the solubility equilibrium equation. Yes? But if we're told that the concentration of PbI2, actually, let's not even do a race table. If the concentration of PbI2 is 1.52 times 10 to the minus 3 molar, what is the concentration of lead and what is the concentration of iodide?
1.52 times 10 to
Yeah. This is a 1 to 1 to 2. So the concentration of lead is 1.52 times 10 to the minus 3, because these are 1 to 1, right? This is 1.52 times 10 to the minus 3. And this is 1.52 times 10 to the minus 3. And then the concentration of iodide would be how much? Double that, 2 times 1.52 times 10 to the minus 3. Okay, so we now have 1.52 times 10 to the minus 3 times 2. So we get 3.04 times 10 to the minus 3. So that's 3.04 times 10 to the minus 3. Now, how would we find the KSP? Yeah, how would we do the KSP? You multiply lead and iodide, but first of all, you'd have to start by writing a KSP expression. So that would be, what is the KSP expression for this reaction here? Concentration of lead 2 plus concentration of iodine squared. Oh, look at that. So now we have 1.52 times 10 to the minus 3 times 3.04 times 10 to the minus 3 squared. 4.6208 times 10 to the negative 6, which would then be 4.62 times 10 to the minus 6, and that would be your answer. Look, you're already halfway through section 3.3.
What?
Because 3.3 is all about doing the math, and you guys have already done like KEQ, right? And you've done KAs, and KSP is just another K. So if you're like, oh, okay, well, if I know the concentration of, if the only thing that's weird here is what the heck do they mean by molar solubility? That just means how much will dissolve, which means what is its concentration? Yeah? So if you know the molar solubility, you know the concentration. And if you know the concentration, then you know the concentration of the ions, because you guys are geniuses. So smart, you all. Yes?
So it's saying the molar solubility, so like the concentration of PbI2
Is 1.52 times 10 to the minus 3. So that's really the only new piece there, is calling it the molar solubility. Okay? All right, a student titrates. Okay, they titrate 10 ml sample of well water to find out the chloride ion concentration in the well water. And they titrate it with 11.97 milliliters of 0.1 molar silver nitrate to precipitate the chloride ion in the well water. What is the concentration of chloride? Are we looking for a precipitation equation, or are we looking for a solubility equilibrium equation? Precipitation equation, because nowhere in here does it say anything about solubility equilibrium. Nowhere does it say anything about KSP, right? Titrations always use the precipitation equation. Yes.
When you're writing like the ratio, we have these ones, right? Yeah. And so can we just write like 1 to 1 to 1?
Yes.
Yeah, see?
You don't even have to write it. You can just be like, concentration of H is equal to concentration of HCl. Do you know what I mean? Yeah, totally fine. Could you guys solve this question? Do you remember how to do a titration equation? Or actually, before that, let's write our precipitation equation. And the only thing that's a little bit complicated about this is that we have given you silver nitrate, which is a, excuse me, a compound. And we've given you the chloride ion, which is just an ion. And that's because the chloride ion is dissolved in water, and maybe some of it was sodium chloride, and maybe some was calcium chloride, and maybe some was magnesium chloride. You just don't know where that chloride came from. Okay, so we're not pairing it with a particular cation. What do we know about nitrate? Nitrate is always soluble. And if it is always soluble, what type of ion will it be? It'll be a spectator. So if you have one reactant that's a compound and one reactant that's an ion, but you happen to know that in the compound you have a spectator ion, what kind of reaction should you be writing probably? Yeah, write a net ionic. Okay, so we're going to write the net ionic precipitation equation, okay? And a precipitation equation always has the solid on the right-hand side. And it always has its ions on the left-hand side. Who are the two ions that are reacting here? Tell your partner. Ag. Ag and Cl. And then it gives you Ag, Cl, solid. Are we happy with that? We need our charges. Are we happy with that arrow?
Yes.
Yes. Precipitation equations always have a one-way arrow. What information do you know about the silver ion? Read the question. What information do you know about the silver ion? It has the same concentration as the AgNO3. Okay, so the concentration of silver is equal to the concentration of AgNO3, which is equal to 0.100 molar. What else do we know about the silver? Not the same concentration. We also know that we have how much of it? 11.97 milliliters. Which is how many liters? 0.01197 liters of 0.100 molar Ag. What does of mean? Of means multiply. Oh, look what we're going to do. We're going to say 0.01197 liters of 0.100 moles of silver per liter. So that gives us 0.001197 moles of silver. What are we being asked for in this question?
Concentration of chlorine.
Concentration of chloride. What can we figure out about the chloride?
The same as silver.
It's the same as silver because these two guys are 1-to-1 ratio. So therefore, the moles of chloride equal the moles of silver. And so that's 0.001197 moles of Cl minus. But we weren't asked for moles of Cl minus, we were asked for concentration. Well, hang on a second, let's think about that for a second. The concentration of chloride in the well water is, well, we want our moles on the top for sure, right? So we got 0.001197 moles. Do we want to divide that by 10 or by 11.97 or by 21.97? Do I want 10? Do I want 11.97? Or do I want 21.97? I got some people saying 10. I got some people saying 21.97. Yeah. How much chloride is left after this reaction is complete in our 21.97 milliliters? How much chloride is left? 0. So what's the concentration in 21.97 milliliters? 0. We want to know what was the concentration in the well water, right? So always use your original volume here. Never combine your volumes in a titration. Never. Never combine volumes in a titration. Okay, and that kind of gets us to the end of today. You guys can do some review for your test tonight, but I would also like you to try. Did you do page 20? No. How about we do 20, page 20, number 1A and number 2A. That still gives you time to study your acid-base stuff. It's okay, it's just page 20, number 1A and number 2A. If you want to do more, if you have time tonight, if you're like, I've studied acid-base, I'm sick of it, do more if you have time.